Good morning, ladies and gentlemen. I am Dr. Kherroubi, and today I am glad to present AUTODRAITEC, which is an AI-based system that is deployed on the road infrastructure to support the driving of connected and autonomous vehicles. This work was presented at the 35th IEEE Intelligent Vehicle Symposium and at the 33rd International Joint Conference on Artificial Intelligence. In nowadays, tremendous research efforts are being invested to develop connected and autonomous vehicles technologies. This interest is increasing because of their potential in improving driving safety and efficiency. Indeed, and according to studies, autonomous vehicles technology could reduce the accident rate close to zero, increase traffic flow by up to 35%, and improve energy efficiency by 4 to 10%. However, current autonomous driving system architecture are based solely on onboard components and hence are facing challenges of limited perception range and accuracy, limited onboard calculator, and the coexistence of human-driven vehicles. To overcome these challenges, the road infrastructure has become a key enabler to achieve full autonomous driving by providing extended perception capabilities, higher computational power, and shared functionalities. For that reasons, we designed AUTODRAITEC, a system which will be deployed on the road infrastructure to provide speed recommendation for connected and autonomous vehicles. The system is comprised of a sensors module with an industrial computer. The software of the system includes a perception framework, which provides a detection accuracy of 98%. We propose a hybrid machine learning approach comprised of a supervised learning classifier with a deep reinforcement learning agent. The supervised learning classifier is trained to predict the behavior and intention of human drivers in a specific driving situation. This prediction is used as an input state for the deep reinforcement learning agent that will provide the speed recommendation as output action for the connected and autonomous vehicle. The advantages of this architecture are: first, it improves the situational awareness thanks to the increased perception range and the stationary nature of the road infrastructure. And second, it improves the explainability of actions provided by the deep reinforcement learning agent through the information provided by the driver intention model. We simulated our approach for 10,000 highway on-ramp merging episodes and compared its performance with the benchmark human driver. Results show that the system increased safety distance by 30%, eliminates collisions, reduce the number of emergency braking cases, increase average speed by 15%, and increase traffic flow by 0.3%. This means that the system could improve driving safety and efficiency while preserving the traffic flow fluidity. To test the performance of AUTODRAITEC, we developed and integrated a 1/18 scale testbed. The driving geometry is similar to a real-world highway on-ramp merge location at reduced scale. At the first step of our demonstration, we emulated the following collision case between human drivers. The drivers on the merge lane and the highway arrive at the same distance to the end of the merge zone, which generates a conflict and lead to a rear-end collision. In the following, we reproduce the similar accident conditions and use AUTODRAITEC system to provide speed recommendation for the vehicle on the merge lane. Clearly, we observe that the merging is safe. After analyzing this situation, we found that the driver intention model predicts the intention to yield for the highway driver earlier at the entry of the merging zone. Based on this prediction, the deep reinforcement learning agent provides speed recommendation for the merging vehicle to accelerate and increase its speed. The confidence of this prediction increases, and the vehicle then merges with a high safety distance from both the preceding and the following vehicles. To check the robustness of our system, we emulated the same collision condition but with more aggressive driver. Like the first case, this situation generates a conflict and lead to a rear-end collision. We now use AUTODRAITEC system to provide speed recommendation for the vehicle on the merge lane. We observe that the merging with AUTODRAITEC system is still safe, although the driver is more aggressive. After analyzing this situation, we found that the driver intention model predicts the intention to not yield for the highway driver earlier at the entry of the merging zone. As in the first experiment, the confidence of this prediction increases, and the deep reinforcement learning agent provides speed recommendation for the merging vehicle to decelerate in this case rather than accelerating. The vehicle then merges with a high safety distance from both the preceding and the following vehicles. For both demonstration cases, we evaluated the safety distance at the acceleration lane. We clearly observed that AUTODRAITEC system managed to keep a minimum safety distance of 20 meters early at the entry of the acceleration lane with both the leading and the following vehicles. Through this speed recommendation provided by our system, the safety distance increases progressively until the end of the acceleration lane, where the autonomous vehicle is compelled to merge at the latest, and therefore the risk of collision is higher. In summary, we presented a demonstration of a machine learning based system that is deployed on the road infrastructure to support the driving of connected and autonomous vehicles. We showed how this system could improve driving safety and efficiency. As future perspectives, the system should be scaled to further driving scenarios and use cases.